5 past 6. So yeah, good evening, everyone, and thank you for joining. I'm Evangelos Yfantidis, current chair of the second Young Member Subcommittee, and today I have the pleasure of welcoming you to our evening talk on innovative frictional damping devices and their implementation as a retrofit system for existing industrial buildings. This is a hybrid event taking place in Paxley Lecture Theatre at the University of Bristol in person and online through Microsoft Teams. And at this point, I would really like to thank the University of Bristol for providing a venue for this talk tonight and giving us this opportunity. So before we begin, please let me go through some housekeeping rules and important information. So for those joining us online, I will first kindly ask you to keep your video cameras off and microphones on mute for the duration of the presentations. And just to clarify, this is applicable only for the audience. So I would like to invite the speakers to keep their video cameras on if possible. After our speakers finish with their presentations, we will have some time for a Q&A session in the end. But in the meantime, please feel free to type any questions you might have in the chat. Please also note that this talk is being recorded and will be later uploaded on our second YouTube channel. And therefore, by dialing into today's event, you consent that any views or information you share will be made public. For those being present in the room with us, I will kindly ask you to keep your mobile devices in the silent mode. And bear in mind that you will have a chance to ask questions during the final Q&A session in the end. Also, please note that there are no fire alarm tests planned for this evening. So in case the fire alarm goes off, we'll need to evacuate through the main building entrance, which is close to this room. So just a brief introduction about SECEND, the Young Member Subcommittee. For those who might not know about us, SECEND is the Society for Earthquake and Civil Engineering Dynamics, and is a specialist branch affiliated with the Institution of Civil Engineers. The aim of SECEND is to foster collaboration among the civil engineering community and organize professional development events focused on earthquake engineering and structural dynamics. Particularly, the Young Member Subcommittee is a diverse group of young civil engineers from both academia and industry that work on initiatives on behalf of SECEND. On the left, you can see a picture of some of our current and past group members, where we assisted with the organization of the SECEND 2023 conference that took place in Cambridge back in September. I would also like to make a quick announcement. Every year, SECEND runs a funding scheme called the SECEND Fund, where we award up to £1,000 to individuals or teams who are seeking to further their studies, research, or career in the field of engineering dynamics, or they're undertaking a project that will promote or lead to advances in this field. We consider applicants of all nationalities with a valid SECEND membership, and there are no restrictions on academic or employment status, as well as there are no age limits. The SECEND Fund 2024 is now open, and the application deadline is 31st of July. So if you're interested, you can find more about this on our SECEND website, including the required application forms, as well as terms and conditions for applying. So now moving on, I will now introduce our two speakers for this evening. Our first speaker is Eleonora Grossi. Eleonora holds a master's degree in civil engineering from the University of Ferrara in Italy, and very recently completed her PhD in engineering science at the University of Ferrara. Her doctoral research focused on developing a damping system for the seismic protection of precast reinforced concrete buildings, combining concepts of tribology, mechanical design, and numerical analysis. Eleonora is currently a postdoctoral fellow at the engineering department of the University of Ferrara. Our second speaker for this evening is Yichen Zhang. Yichen is a research associate at the University of Bristol and holds a PhD in civil engineering from the University of Bristol. His research interests are in earthquake engineering and structural dynamics. He's also currently involved in the LASI project, focusing on the residual displacement reduction design of a low-cost isolation system. Now, without further ado, I will hand over to Eleonora on the talk so we can start. Eleonora, could you please kindly share your screen?
Yes. Give me a second. Okay. Can you confirm that the screen is sharing?
Yes, the screen is being shared now.
Okay, perfect. So, good evening to everyone. And first of all, thanks to Evangelos and Yichen for organizing this event and inviting me. I am Eleonora, and I'm here to talk about double damper, bidirectional rotational friction damper for the seismic retrofit of precast RC structures. First of all, why I focused on precast RC structure? Mainly because the majority of those existing buildings have been designed for gravity loads only, meaning that they have a poor or absent connection between structural elements and a poor elements detailing, especially for the columns. This structural typology has been usually associated with industrial building, like the one that you've seen here, but they're also used to construct commercial buildings, schools, shopping malls, gym centers, and swimming centers. All of these structures are strictly connected with a local community, so what happens when an earthquake arrives and damages it? We have an example of it 12 years ago during the 2012 Emilia earthquake that took place in Italy, actually near my hometown. During this event has been quite particular because the hit area is a high productivity area in Italy with a huge number of vulnerable precast RC structures. And the combination of this vulnerability with the exposure affected more than 500,000 people, producing 28 casualties, the closure and relocation of the 58% of the local activities, and more than 700 cubic meters of rubble, for a total of 13 billion euros of global damage. Usually, when retrofitting precast RC structure, we focus on the strengthening of the element connections and the introduction of additional structures to stiffen the structure and the introduction of energy dissipation system. However, these retrofit techniques are not always efficient and can be quite invasive, both under the construction work point of view, but also from the architectonical point of view. So with the need of combine the need of the connection improvement and minimally invasive dissipation devices, the research community started to develop the dissipative connections, like the one that you see in these figures. They proved to be quite efficient in the reduction of base shear and top displacement, but they are monodirectional. So if we have a building like this one that I'm showing you here, in which the main frames are not properly connected with orthogonal beams, the allowable position for the device is limited in the in-plane direction of the main frame. So if an earthquake arrives, the direction of the main frame is protected, but the other one not. So my idea was, what if this dissipative connection is bidirectional? So if we have the same building and an earthquake arrives, we have the direction of the main portal frame protected as before, but this time also the other one is protected. And this is where the idea of double dam came from. And I'm here to talk about the journey of its development, starting with its conceptualization to the prototyping, mechanical and numerical study. First of all, what is double damp and how does it work? Well, double damp is a rotational friction damper. It's constituted by an assembly of layer steel plates connected with stud bolts, as you can see in the picture in here. This geometry is kind of particular because it's a movable geometry. So when the device starts to move with a general displacement like in this one, I can decompose this displacement with a longitudinal and a transversal component. And here there's a key point for this device, because we observe that the longitudinal component is responsible for the activation of these two dissipative areas, the ones that I colored with the blue color. And the activation of these two dissipative areas generates the longitudinal activation force F act X. Similarly, the transversal component of the deformations is responsible for the rotation, so the energy dissipation in these two red areas. which generates the activation transversal force F act Y. Now, why this is a key point? Because given the fact that this type of activations is decoupled, meaning it means that I can implement in a simplified way this device like two dampers in one. As I told you before, double damper is a dissipative connection, so it has been designed to be installed as a beam-to-column connection. But to maximize its double damping capabilities, its longitudinal direction must be installed so it has the same orientation of the in-plane frame direction, the in-plane direction of the main frame, and its longitudinal component must coincide with the out-of-plane direction of the main frame. This way, when the frame starts to oscillate, I can limit the displacement in the in-plane direction and in the out-of-plane direction, like in these two figures on the right. So first of all, I needed to understand if this device could be actually effective in a vulnerable precast structure. So I took as a case study this building that you see in here, which is a single bay, single story structure with a square plant of 15 meters for 15 meters and 7-meter height. It has square columns with a perfectly symmetrical detailing, I-shaped beams, and P-slab roofs. As you can see, this structure doesn't have orthogonal beams that connect the main frames, so the allowable position for the device are limited with the in-plane direction of the main frame. This building has been located in L'Aquila, which is a high-risk Italian seismic zone with a soil type B and importance class 3 according to the Eurocode 8. I performed nonlinear time history analysis using 7 couple of spectrum-compatible ground motions. You can see in here the graph for the spectrum compatibility. I implemented this building in OpenSeas. I model the beams as elastic beam columns element. The columns I use fiber sections, and for the roof I used a diaphragm constraint. The double damp has been implemented using a zero-length element with associating 2 steel 01 materials, one for its longitudinal direction and one for its transversal direction. You can see in here how the numerical calibration of the elements coincides with the analytical formulation of the device that I took for reference. Before assessing if this device can be actually beneficial for the structure, I perform a sensitivity analysis to identify the better configuration for this device. So I varied its activation forces and its initial stiffness, and then I perform an importance analysis using a multi-criteria decision-making approach, and with the goal to identify the combination of activation force and initial stiffness that at the same time minimize the base shear, interstory drift, the column-based rotation, and columns shear. I obtained this graph that you see in here, where the dark area corresponds with the unfeasibility of the device. Then the area starts to get lighter as the performance improves, until I reach the optimum configuration, which is this green dot in here. Here you can see the comparison in terms of dynamic performance of the case study without and with the double damp, which is labeled in here as TD. The blue bars are associated with the in-plane directions and with the orange bar with the out-of-plane direction. You can see that the base shear, starting from the top left, has been decreased of around 28%, while the interstory drift decreased of around 62%. Similarly, also the columns-based rotation has significantly decreased. So in this case, with the double damp, the columns are not yielding, and while the concerning the share of the columns, also in this case, the demand has decreased, but in this case, the columns are quite stiff. So there wasn't really a problem in terms of share. But in any case, with these graphs, you can see that a significant improvement in terms of dynamic response. And you can visually see that with this video that I took of the dynamic response of the case study using the Mirandola ground motion record that happened during the 2012 Emilia earthquake. So on the left, you can see the configuration without double dump, and you can see that the movement are bigger, and also you can see these blue circles, which are associated with the yielding of the columns. This doesn't happen with the double dump configuration. So now that I read my device, I started the prototyping process, and in particular, I wanted to identify the better friction interface. And when I say that I wanted to identify a proper friction interface, I mean that its associated friction coefficient should be unaffected by velocity, temperature, and pressure variation. All of these properties are a function of different material, machining process, and superficial hardness and roughness of the two counterbody. So I had some, let's say, some combinations to investigate. For this reason, I conducted a tribological campaign with a tribometer using a pin-on-disc configuration. This test consists of a loaded pin pushed against a rotating disc. These type of tests are quite common in the mechanical field when they want to investigate the combination of different material, different machining and superficial finishing. So it was perfect for my case. However, this type of test can be considered as a scale test. So the pressure applied on the pin and the velocity of the disc must be set so the product between pressure and velocity of this test should be similar to what I expect on my friction interface in a real use condition. So at this point, once I set the pressure and velocity, I just needed to select materials and finishing. So for the pins, I selected 3 different materials: steel, because the device is made of steel, bronze, and brass, which are softer than steel. For the disc, I selected 2 different machining processes, which is turning and milling, obtaining 4 different roughness values each. Then I investigated the shot pinning, which increased the superficial hardness of the steel. And finally, I investigated 2 different coatings, nickel base and zinc base. When investigating the effects of different textures, I focused mainly on turning and milling, and I observed that the best performance is reached with the turn disc with the smallest roughness values, which in this case is 0.8 micrometers. So I selected this disc as the reference for the following test. For the investigation of the different material effects, I investigated the steel pins, bronze and brass on the turn disc, and I observed that the best performance has been reached with the turn disc with the bronze pin. And finally, for the different treatments, I observed that the best overall performance is reached when I used the nickel disc configuration. So considering the last 2 parts, I wanted to investigate a little deeper what happens when coupling nickel disc and nickel pin and nickel disc and bronze pin. So in here, you can see the result with this double axis graph. On the vertical axis, you can see the coefficient of friction and the associated sliding force, while on the horizontal axis, the sliding time and its associated distance. The purple color is associated with the nickel-nickel coupling, while the orange line is with the nickel-bronze coupling. You can see also that both line has a colored area above them, which is represent the standard deviation over 5 different. You can see that the nickel-bronze config coupling has a smaller area, meaning that this coupling is more steady. So and also you can see from this graph that is quite a straight line. So I decided to use this coupling as an interface to prototype my device. So as a final process for the prototyping, I manufactured the double dump with an activation force that ranges between 10 and 20 kilonewtons, a maximum displacement of 40 millimeters, and overall dimensions of 30 for 20 centimeters. You can see on the left how the core central connection and sub plates are all interlocked with the friction pads and all placed together with the final assembly on the right. So at this point, I proceeded with the mechanical test to assess if the damping capability of the device was steady and repeatable. So I performed a bidirectional test. I actually came there where people is attending at the University of Bristol. I performed this test. This test at the heavy and light structure laboratory. You can, if someone there can recognize the strong flooring here. And the experimental setup consisted of 2 actuators tuned together to apply simultaneously to displacement in 2 different directions. And I applied several FVDTs to double check the displacement applied by the actuators and any misalignment of the device. And finally, I instrumented the stud bolts of the device. This was to monitor the actual force, the actual load on each bars. To achieve that, I inserted these cylindrical strain gauges inside a hole that I drilled within the stud bolts, and you can see here the wires coming out. The testing protocol consisted of monodirectional test and bidirectional test. For the monodirectional test, I applied a sinusoidal waveform to assess the monodirectional real use condition for the device, a triangular waveform to identify any influence of the sliding velocity on the performance of the device. And finally, I performed a bidirectional test using a cloverleaf waveform to assess the bidirectional behavior of the device in a real use condition. Here you see the result of the monodirectional test. In here you see the hysteresis cycles. The blue lines are associated with the longitudinal direction and the orange lines with the transversal direction. You can have a little reminder up on the top right of the slide. You can see that the hysteresis cycles obtained at a smaller frequency and high frequency are quite similar, and this is quite important because the device can act in the same way independently from the frequency content of an earthquake. This is also confirmed when computing the equivalent damping using Jacobson formulation. You can see that the values along the longitudinal and transversal direction are quite the same and are almost unvaried. When focusing on the sliding velocity influence, you can see that the hysteresis cycles are slightly more rectangular. This is because of the type of sign-off that applied, and also that there is a quite small influence as a function of the rotation velocity. You can see here that the friction coefficient that I evaluated is likely bigger at the smaller velocity. In here, you can see also that I computed the friction coefficient in 2 different ways. The lines with the triangular marker I computed the coefficient of friction starting from the energy dissipated per cycle, while the circular marker I computed from analytical formulation. and the dashed line is just the average between the two. You can see that independently from the methodology, I achieved the same number, which is quite promising. And also that the number that I obtained, which is around 0.4, is the same that I obtained from the tribological test, which is good. And this is what happened when I applied the bidirectional waveform, which in this case is a cloverleaf. You can see that the hysteresis cycles are still rectangular, which is good, and they are also unaffected by the frequency increment. Only this time the transversal direction is slightly less rectangular, so the equivalent damping is slightly smaller than the monodirectional test. However, you can see that the damping coefficient are still high, and also there is not such a high variation during the test. So after after the mechanical test, I assessed that the device can be quite effective in terms of damping, and I wanted to reproduce its behavior numerically. More precisely, I wanted to reproduce the rotational friction interface behavior. So first of all, how does a rotational friction interface behave? According to the literature, a circular rotational friction interface, which is exactly my condition, starts to rotate not when reaching a sliding force, but a sliding moment. And this sliding moment is a function of the coefficient of friction, the vertical load, but also of the geometry of this area. You can see here that it's a function of the outer and inner radius of this area. So I simplified this formulation, computed an equivalent radius that I wrote as RAQ. So let's consider now having two bodies rigidly connected with each other and with a center of rotation. Let's imagine now to apply a vertical load FB and a half over each body, and imagine also to have a friction coefficient between the body and the surfaces. We can say that from physics that the sliding force of this body when it moves is a product between the friction coefficient and the force that applied. However, since everything in here is connected with a center of rotation, when this body moves, it follows the circular path of radius RAQ, and following the circular path, it generates the sliding moment MS. So this exact behavior is what I wanted to recreate numerically. And to do that, I use the flat slider bearing element. So I model two beams with a stiff geometry. You can see in here the number 4, 1, 3, and 6, 2, 5. All these points are perfectly aligned, and points 1 and 2 are connected with each other in order to recreate this center of rotation that I showed you before. So when I apply the axial force FP and a half over all my external nodes, and I start to rotate the element with node 5, 2, 6, its rotation follows the circular paths around the node 2. This is how I numerically implemented my rotational friction interface, and I used it to reproduce all my devices. So I used that approach to reproduce the dissipative area, which you can see now numbered in here, DA1 to DA4, is exactly like in the picture that I showed you before. And also in here you can see that I call all the elements of the device following this axonometry drawing, and the colors are the same in here. So I model all the elements of the device using elastic beam elements with the same geometry that you see in the prototype that I manufactured. At this point, I just needed to associate to my friction interface a constitutive friction law, and OpenSys allows me to associate different friction laws to to the flat sliding bearing element. First of all, I investigated the Coulomb friction model in which the friction coefficient is considered constant. You can see here also the comparison between the numerical and experimental test. The numerical tests are here with the bold continuous line, while the experimental tests are the dotted lines. You can see that already with this simple constitutive model, the matching is quite good, especially for the monodirectional test. While for the cloverleaf test, there is still some a gap in here at the maximum displacement. However, overall, the comparison is really good. So I tried a different constitutive law for the friction, and I investigated a velocity-dependent friction model. This model is a function of a friction coefficient at a low velocity, a high velocity, of a parameter A, which does simply define the curvature of this curve and of the sliding velocity. You can see that the comparison between the experimental and numerical test is slightly better than before, especially for the cloverleaf test. And this was quite good for me because I can use this tool to develop a virtual lab tool. And this is quite efficient because I can improve the design of my device. So for the conclusion, I can say that double dump can significantly improve the dynamic performance of an existing structure, reducing the base shear and interstory drift, avoiding any structural damage. The mechanical tests show me that its hysteresis cycles are quite steady and reliable and have a good damping capacity, both in the monodirectional and bidirectional test. And finally, the numerical model that I implemented well represents the behavior of the device, especially for the rotational friction interface, and is quite useful to develop a virtual lab tool for further investigations. So for this further investigation, which is part of it, I am doing it right now. I am focusing on an update of the experimental setup and also on the stud pull monitoring system. Moreover, to assess what the interaction between the device and an existing structure, the Yichen table tests are going to be performed next year with an ARIES project, which is an ongoing project. Finally, I also need to investigate what happens when I select a different case study with a different typological and topological structural configuration. And finally, a life cycle assessment to evaluate how my device, how double dump can improve the sustainability and resilience of a building or a cluster of buildings. So thank you, everyone. And also thank you for the University of Bristol for helping me developing a part of this device.
Thank you very much, Eleonora. That was a really interesting presentation.
Thank you.
Yichen. So now we will begin our second presentation.
Okay, I'll stop sharing.
Yep. So let's go here.
Okay, then let's talk about the scale device. The full name of the scale device is sliding case on inclined deflecting cantilever device. This name is given based on its configuration. So you will say a sliding case, you will say the cantilevers and the slopes at the top of at the tip of the cantilevers. So the scale device is proposed for post-tension frames. So it's actually in a context of self-centering structures. This research was carried out in the past 4 or 5 years by my supervisors, Nicholas Alexander, Raphael Derisi, and me. Okay, so first I have to give a brief introduction about this device, and then it's about the scale device itself. And after that is a PET scale frame. It's actually the application of the scale device in the frame. And we will focus on its seismic behavior and the seismic design. Finally is a very quick case study. Okay, so first, why do we propose this device? As I said, it's actually proposed for post-tension frames is for self-centering structures. Self-centering structures is a type of structure that could, there will be no residual displacement, or the residual displacement is ignorable after earthquakes. So these structures could be accessible after earthquake immediately. And to achieve this self-centering capability, the hysteretic curve of self-centering structures would be located at the first and third quadrant only. So let us look at the PT frame, the post-tension frame. The PT frame here means the cable and the columns are pinned together by cables. So the hysteretic curve of PT frame would be like the first figure. It's nonlinear elastic. You can see that its hysteretic curve located at only the first and third quadrant. So it's actually inherently self-ring center. But there isn't hysteretic damping in PT frames. If we don't add any damping devices, the paired PT frame would have a large displacement in earthquakes. Alternatively, if we decide to target displacement, we have to use a large sections for the PT frame. So we have to add damping devices. There were some options like metal dampers or frictional based damping devices. And these kinds of damping devices has a parallelogram shaped hysteretic curve. For example, the second figure is a conceptual hysteretic curve of typical friction-based damping devices. There is an activation threshold. It is point B in the central figure. Only when the external force greater than this point B, these types of damping devices could be activated. This means if we design a really high activation threshold for the damping devices, the device could be, will be activated only in large events. But if we design it at with a small value, the devices will not provide much damping. This is the first point. The second point is that activation threshold would inhibit self-centering. So, because as I said, if we want the frame could recenter, its hysteretical must be located at the first and third quadrant. So after adding the damping device, the hysteretic curve of the entire frame would be like the third figure. If we want the point C at the first quadrant, the point A in the first figure must be greater than the point B in the second figure. In other words, the activation threshold requires a higher strength for the PT frame. Okay, beyond these 2 points, if for the metal damping devices, residual displacement exists after, residual stress exists after earthquakes. For frictional damping devices, mirroring and ensuring the correct normal force is problematic. So I would say the activation threshold is a feature of traditional dampers. Could we eliminate it? We propose this device, the scale device. The scale device follows the schematics in the left figure. And by following this, it will perform a hysteretic curve in the right figure. So you can say they have a triangular shaped hysteretic curve. Because its hysteretic curve is triangular shape, so there isn't activation threshold. It will not inhibit self-centering. There isn't residual stress after earthquakes, and no initial normal force required. And the scale device could perform two types of hysteretic curves. The one type is the curve following the solid line, the curve located in all four quadrants. The other type is that the curve only located at the first and the third quadrant. The unloading trace would follow the dashed line. These two types of hysteretic curves are controlled by parameters of the device. Okay, then is a configuration of the scale device. So I have a 3D model right here. So there are three main components for this device. This is sliding keys. You can see four slopes on the sliding keys. The sliding keys will be attached below the beam. And the other part is some cantilever bars. The cantilever bars will be fixed on the ground or at the top of a support column in a structure. And at the top of these four cantilever bars, there are another four slopes. So in the frame, it will be like this. And when the beam has a horizontal displacement, the sliding keys will drift in this, I would say, in-plane direction. And the slope on the sliding keys will sliding against the slope at the top of cantilever bars. Yeah. So by following this schematics, the device will perform hysteretic curves like this. And its hysteretic curve could be estimated by equations. We can use equation to estimate the loading stiffness of the devices and its equivalent hysteretic damping. These two critical properties are controlled by three parameters. The one is friction coefficient. The second is slope angle beta. And the third one is the tip stiffness of the cantilever bars. Okay, so we did physical tests at the Heavy and Light Lab in University of Bristol. And all of the specimens are 1/4 scaled specimens. And these specimens was subjected to quasi-static cyclic loads. And during this test, technicians Steve, Pete, Guy, Mark, and Mick Choi provide professional technical assistance. Okay, so we designed two groups of specimens. The first group has two specimens. They are denoted as gate A and gate B. These two specimens are corresponding to two types of hysteretic curves. So they are for conception verification. The second group has 6 specimens. These 6 specimens have different friction materials, have different sliding angles, different tip stiffness for cantilever bars. There are 2 loading protocols. The protocol A is an amplitude increasing loading. The protocol B is for fatigue test. The fatigue loops has 100 cycles. Okay, then let's look at the test results. First is about the conception verification. So you can see that skate A and skate B perform stable and repeatable triangular shaped Hasse-Rayleigh curves. And they are corresponding to two types of Hasse-Rayleigh curves. Then is empirical sensitivity analysis. I would say the most important information I would deliver from this page is that the brick lining specimens, I mean the specimens using steel against the brick lining as sliding surface, show most smooth Hasse-Rayleigh curves. The specimens with brick linings are the first figure and the last two. And the red three figures are the behavior of specimens with steel against the metal pads. Another information from sensitivity analysis is that the loading stiffness and equivalent damping ratio can be tuned by adjusting the parameters of the device. Okay, finally is fatigue test results. The first line, the upper two figures, are the Hasse-Rayleigh curve and force time history of a steel against brick lining specimen under fatigue loops. The lower two are the Hasse-Rayleigh curve and force time history of a steel against a steel specimen. So you can say that the steel against the brick lining specimen exhibited the most stable Hasse-Rayleigh performance without any strength or stiffness degradation. But the specimens with metal pads had much more irregularity in force and stiffness, but there isn't stiffness degradation were found, although it's not stable, but there isn't stiffness degradation. So if we want a more stable behavior, we need steel against the brick lining. However, we have to attach brick lining pads on the surface of the steel pads. So it's definitely increase one more manufacturing process. So I would say it depends on the design target. Okay, these are about the skate device itself. Then let's look at its application in the post-tension frames. They named this frame PT skate frame. In PT skate frame, the skate device would be below the beam, and the height of the skate device actually depends on, decided by the required stiffness of the cantilever bar. So the height of the ski device could be shorter than the height of the floor. So for those cases, we need a support column to support it. But the support columns are mainly for warehouse structures. The structures have a really high floor. Okay, we built a model, numerical model in OpenSys. And they tested lots of frames. So the Hasse-Rayleigh curves. So let's look at the Hasse-Rayleigh curves of the PT skate frame first. So the PT skate frame will perform a curve like the below figure. So you can see that it performs a dual triangular flag-shaped Hasse-Rayleigh curve. The Hasse-Rayleigh curve of the PT skate frame is actually the curve of the PT part plus the curve of the skate part because they are connected in parallel. Okay, here I will present the results of 700 frames. These 700 frames have different skate parameters, but the PT part is the same. The skate parts have different loading stiffness K, different mu, and beta. 7 pairs of ground motions at collapse limit state were utilized in analysis. Then let's look at result directly. So here I presented three figures as an example. The first figure is about drift ratio. The drift ratio is presented by different colors. The blue color means a lower value, and the yellow color means a higher value. The x-axis and the y-axis are parameters of the device. The second figure is a base share of the PT part. The third figure is a base share of the skate part. So you can see that the response of the PT skate frame is actually loading stiffness controlled. I mean, controlled by the loading stiffness of the skate device. If we use a higher loading stiffness, the peak drift ratio of the frame would be smaller. Correspondingly, the base share of the skate part will be smaller. However, the base share of the skate part would be larger. So that means the design of the PT skate frame should be considered as a trade-off between the peak drift response and the base share of the skate part. So this means the design of the PT skate frame requires a performance-based design. So we choose direct displacement-based design for these structures. So I will talk about it later. Before this, let's look at the self-centering behavior of the system, because self-centering is a main point to propose this new device and frame. Okay, so the hysteretic curve of the PT skate frame is like here, like this. I presented one case. So it's just to show that the hysteretic curve of the PT skate frame will be not always at the first and third quadrant. For example, this case. In this case, when the peak drift ratio is less than 1.8%, the hysteretic curve will be located at the first and third quadrant only. But if the drift ratio over this point, the hysteretic curve would drop down to the second and the fourth quadrant. That means from quasi-static view, it will not recenter. So we define these critical points as self-centering quasi-static threshold. So is it a problem? Let's look at the 700 frames we tested, because each frame was tested by 7 pairs of ground motions. So actually we have around 10,000 cases. In these 10,000 cases, there were around 900 cases where the transient peak drift ratio was over the self-centering quasi-static threshold. We found all cases recentering. So that means the self-centering quasi-static threshold will be not a problem, at least from this analysis. But of course, this point needs more analysis to be confirmed. Okay, then let's look at the design of the PT skate frame. The DDBD design, we choose this design method to design the PT skate frame. And one of the critical logics of the DDBD method is defining a substructure for the real system. I mean, the real system is normally a nonlinear system, and we need to define a single dwarf linear substructure for that structure. So we will use the substructure to estimate the behavior of the nonlinear system. So this is one logic, a core logic of DDBD. So if we want to define the substructure, we need to calculate the equivalent damping ratio. One method is area-based method. The method is like this equation. So this method, I would say it's actually the Jacobson's method. Okay, but this method normally leads to, frequently overestimate the equivalent damping ratio of the system. That means the design following this method may be at the unconservative side. So this method normally needs a correction in the design process. So we investigated if it's the same for the design of the PT scale frames. We built a simplified hysteretic model so that we can test thousands of frames. The model could represent thousands of frames, the real frames, but it's easier to be tested. Okay, and the logic of this investigation is quite simple. It's something like we have a nonlinear system with certain parameters, and we identify a substructure for that model, and we make these two models subjected to the same earthquake ground motions, and then we compare the peak drift ratio. If the peak drift ratio is the same, we can say that the substructure is accurate. So when we do this comparison, we calculate a factor eta. Eta is this peak displacement obtained from nonlinear analysis, that is D nonlinear, over D spectrum. D spectrum is a displacement, peak displacement from elastic analysis from that substructure. So if eta equals to 1, the substructure is accurate. If eta is greater than 1, it means the substructure is overestimated the equivalent to the hysteretic damping, and it will make the design at the unconservative side. Then let's look at the results. Eta in far field or near field null pose events is greater than 1 for most cases. That means eta needs corrected. And we find that the variation of eta is in a narrow range. It means we can consider using a uniform correction factor for all the cases because the variation is in a narrow range. Then is eta in near field pulse-like events. We found that eta is much more scattered. It could be greater than 1 for some cases. It could be less than 1 in other cases. That means eta still needs corrected in near field pulse-like events, but this correction factor must consider the parameters of the frames because the variation of eta is scattered. So we introduce a correction factor into the elastic design spectrum. So you can say that the elastic design spectrum will have one more factor, is say E. For the size where far field or near field null pose ground motions are considered, say E is equal to 1.13. It is an uniform factor. But for the size where near field pose-like ground motions are considered, we have to find the say from a chart. And this chart will be defined by several curves. And these curves consider the parameters of PT scale frames. Okay, so by using this method, when we design PT scale frames, we can follow the typical DDBD method. There is only one difference. It is the elastic design spectrum is different, and there is one more factor. Okay, so these are about the PT skate frames. So finally, I have to quickly talk about a case study. We proposed a PTPW skate structure for industrial structure systems. The PW in this name is precast warehouse. So this frame is for warehouse structures. And we designed a prototype industrial building located at L'Aquila, Italy. And we used the DDBD design method, and we built an OpenSys 3D model in OpenSys. Then we did seismic analysis. We tested 7 pairs of ground motions for this design case. And you can see from the left figure, it is a hysteretic curve of this building, but it's just in the x-axis, global x-axis. So you can see that the frame performs a dual triangular flag-shaped hysteretic curve. The second figure shows the peak drift ratio response of the frame in 2 principal directions. The average peak drift ratio is around 2% under these ground motions. More importantly, the residual drift ratio is ignorable. Okay, so for more details could be found from the journal papers and conference papers. Yes, thank you.
Okay. Thank you very much. Okay, so thank you. So thank you very much, Eleonora and Yichen, for the 2 very interesting presentations. Now I think it's time for the Q&A. So I don't see any question in the chat, but please feel free to type a question in the chat if you want, or you can just raise your hand and ask a question on the call. Is there any question from the room? Yes, sorry. So there is a question in the chat. So it says, thank you to the presenters. My question is for Eleonora. What is the range of slow and fast velocities in your study in terms of the relationship between the friction coefficient and the sliding speed? I assume your kinetic and static coefficients are equal, adhering to Coulomb's law. Eleonora?
Yeah, are you referring to when I presented the experimental result of the mechanical test? I'm asking just to.
Yusuf, are you there?
Okay, at the end. Okay, so the numerical part. Okay. Yeah, let's say that when for the numerical model, so I imagine that at this point, yeah, so in the case, let's say the friction interface that I selected, it's has a small difference between the kinetic and static friction coefficients. In fact, as you can, if you remember, or I can show the slides, or is it a problem? It was a question. Oh. Okay. Yeah, I wanted to say just that the friction interface that I selected has a small difference between the kinetic friction coefficient and the static friction coefficient. So when I modeled the velocity-dependent friction model, there was such difference with the Coulomb friction law. And for the range of velocities is actually the one that I experience with the mechanical test. So it ranges between 60 millimeter per second, per second to 160 millimeter per second.
Okay. Thank you very much. I hope this answers the questions. Okay. If anyone wants to ask anything else from the call, just please feel free to raise your hand or type a question in the chat. We'll make sure to address it. So is there anybody in the room that wants to ask a question? So, moment, let me.
Thank you for both presenters. Eleonora, congratulations for all the achievements. Can you maybe expand on your experimental setup? Have you perhaps included effect of inertia in the setup due to the cyclical loading? And if so, how did you quantify that? Thank you.
With inertia, you mean if there was any, let's say, strange behavior of the device or the weight of the device?
Yeah, because but also because of the movement of the
because I show you just the picture because maybe it's easier to talk over it here. Okay, you can see here this is a fixed element L that grab the device, and also the actuators in here are hinged with two other L elements. So its weight it wasn't so much that deflected the device. And to monitor it, in fact, I put two vertical LVDTs just above the device. So during the oscillation, I could record if there was any, let's say, deflections, and there wasn't any.
Okay, thank you.
You're welcome.
Anybody else in the room?
I have just one question for Yichen, and then I would like a comment from Eleonora. We have seen two dissipation devices. If you were to commercialize both of them, do you think that these two devices, in terms of application, would be competing in the market or not? So what, in terms of use for structural engineering applications, would these two devices look at different application or markets? First to Yichen, and then I would like to hear also Eleonora's opinion on that.
Yeah, so I think these two damping devices may be for two different, I mean, it depends on the design target. So for the scale device, it's proposed for the self-centering structures. So that means for those structures, those structures requires a self-centering feature in earthquakes. So self-centering feature, I would say, is a more advanced feature. I don't know if I can say that. So it means these types of structures, meaning for like critical buildings, like hospital, like schools, and if we talk about the warehouse, possibly the warehouse for critical goods, like goods for hospitals or something like that. But for double damper, I think it's possibly focus on the traditional frames, or say maybe it doesn't require this feature.
So you mean that possibly the application is for different importance class of structures?
Yeah.
SCID would look at higher important class 3 or class 4 structures. Critical infrastructure structures like hospital and so on, while double dump can look at also less category 2 importance structure. Eleonora, do you agree with this? What's your opinion on this?
Yeah, I agree, and I will just add that maybe because my device is bidirectional, it might be more efficient. It's not, I mean, it's not only about the importance class, but it's also on the structure itself. So if it's particularly weak in all the directions of the earthquake, I can limit the displacement more efficiently. I'm thinking like some industrial buildings in which you have some limitation on the space. You have all the like what we call usually secondary elements, but for a building is not secondary at all. We have the piping systems. We have machinery. Things that actually block the application of maybe the SCID device, I can be effective. So we can just work actually focusing on different strengths of our devices.
Thank you very much.
You're welcome.
Thank you. So I have also another question. Obviously, one is, as Yichen was mentioning, oriented for post-tensioned structure that have this capability of rocking. The other one is more designed for traditional structures, as Yichen was mentioning. So looking at the category of rocking structures, Yichen, do you see any other possible application for those kind of special structure that have this capability of rocking, and then they have also pre-stress features, for example, the pump-and-in work. Do you have any idea about possible application in different structure for different structural configurations?
Thank you for the question. Yeah, I think yes, of course. This device is proposed for PT frames, and as a PT frame here is like a conceptual frame. So I would say the PT frame and PT scale frame could be could be for different buildings, like hospital buildings, like teaching blocks, like other things. So yeah, I think there are more application cases. Yeah, just to follow the same logic. Yeah, but of course, maybe the detailed configuration could be slightly different, but the logic, I would say, could be the same. Yeah, thank you.
So another question is, in both cases, I can see that there is a very similar procedure where there is a conceptualization, there is prototyping, there is experimental testing, numerical modeling, and application to real case studies. So both of you, I have a question. Do you think that this model can be exported to industry? Do you think that designing by testing can be a good thing going forward for this kind of innovative devices?
Do I go first?
Yeah, please, Eleonora.
Okay, yeah, I think the methodology that we applied, both we applied, so as you said, the conceptualization, prototyping, mechanical and numerical, it's a base for the development of any new device. You cannot skip these steps, and also the industry should follow these steps. And for the commercialization, obviously, if you it's a part, it's like the end of this, we can say, this chain. So at the end, after assessing that the device that we conceptualize and prototype, it's actually working, we can focus on the commercialization part. It's a part of it.
Yeah, I agree. So yes, so for scale device, for example, the scale device is, I mean, currently investigation is more like in the conceptual side. For practice, it may need more detailed design, and so it's possibly like iterative design or something like that. Yeah, so I think the industry part and the academic part could work together, yeah, to make it more practical, more reliable for the practice. Yeah, I think, yeah, it possibly will be something like that. Yeah, thank you.
I also have a question myself for both of you, actually. So we're talking about the potential markets. So I was wondering if you have engaged in any kind of conversations with any kind of developer or industry experts so that they can actually have a use for your prototypes. Have you engaged in this kind of conversations yet? Or it's still too early?
I think, yeah, it's a good suggestion, I would say. Yeah, I think, yeah, we can start thinking about this. Yeah, yeah. As I said, currently it still need more details. Yeah, yeah.
Okay, for under my point of view, I'm actually already facing this aspect. So I actually nearly funded a startup to actually produce and commercialize the double dam that I just showed you. But for now, the market it's mainly Italian, because as you can see, when I presented the problem, it's more the Italian market, and also because we are just starting now, we just sign things, so it's all it's a little startup baby born just a few weeks ago, so we're just starting slowing, but yes, the commercial part is there.
Okay, thank you very much for this. That's really interesting, and they're both very interesting concepts. So good luck.
Thank you.
One more question.
Thank you to the speakers. For the skid device, since it's unidirectional, right? It's just since seismic motion can come from any direction in terms of.
Yes, it's a good question. Thank you. So yes, this device only works in one direction. So we need devices in both directions in practice. Okay, yeah. And this is one point. The other point is that for any one direction, for example, in this direction, we have a device, because in 3D motion, the beam would have a displacement in out-of-plane direction. So the displacement in that direction needs to be released, I would say. So our consideration is that we will use Teflon pad at the top of the device, and we will have two share case in this direction, in-plane direction. So the in-plane displacement could be transferred to the device, and the out-of-plane displacement could be released. Yeah, so it will be like this.
Yeah,
thank you.
Sense. Thank you.
Okay, thank you. Anybody else in the room? I think there is nothing in the chat. If nobody else wants to ask anything, I think we can just close the session. So thank you very much, Eleonora, for joining us online, for giving the presentation. Thank you very much, Yichen, as well. And thanks once again to the University of Bristol for providing us with a venue for tonight's talk. So thank you very much.
Thank you.
Thank you.